welcome everybody to the next seminar in our series of the Obesity Institute around composite variable bias, presented by Professor Mark Gilthorpe and Ridda, who's one of the PhD students working with Mark. Yeah, just to let you know that the seminar is recorded, and so you are able to go back and watch it again should you wish to. We have got Slido, and the details are available on the screen now. If you want to ask any questions, feel free to add those questions as the speakers are presenting. I'll kind of manage them and make sure they get passed on to the speakers, but also feel free to add any questions in the chat, whichever is easiest for you. We are going to hold all the questions until the end, but please don't hesitate in kind of sending those questions in. And I really want to take the opportunity to encourage people to ask questions. It is quite a complex topic, which Mark and Ridda are going to be discussing today. Absolutely no question is a silly question. And it might not even be a question. You might just want a bit further clarification or something explained in a little bit more detail. We're very, very happy to do that. So please don't hesitate in getting your questions, comments, suggestions over to us. Okay, so I believe you're starting, Mark. Yeah, okay, I'll hand over to you.
And can you hear me okay?
I can, yes.
Good. Okay, so I'm going to first introduce the concept of composite variable bias, and then Ridda will give you a more detailed illustration of it. So the objectives that I'm going to have to cover is to really show how deterministic variables are considered differently within a directed acyclic graph, which is a causal graph. For those who recall from last month's seminar, we use causal graphs to help inform causal analyses. And I'll move on to illustrate some very simple examples of composite variable bias that are readily identifiable as tautological associations. I say they're readily identifiable. They're still considerably overlooked, but it's easier once you start looking for them to recognize them as tautological associations. But then I go on to explain where composite variable bias arises where there are no tautological associations, so it becomes harder to identify these problems. And the point being that composite variable bias arises in the analyses of composite variables in observational research when seeking causal inference, and that causes many challenges and problems for robust causal inference. So deterministic variables are not normally depicted in a DAG. A DAG, the causal diagram, just takes the variables that are variables, probabilistic, have distribution, known distributional property, and links the variables with arcs, saying those are causal relationships, and therefore you're dealing with probabilistic relationships. However, in health and social sciences, many research questions relate to variables or relationships where there's a deterministic component. These may be simply generated, constructed. For example, the simplest being taking a continuous measure and dichotomizing it. There are more complex examples, and the most relevant perhaps to obesity research is that of BMI, where it's constructed from two parent variables, weight and height. Now, there are other situations which are relevant, very relevant for obesity research, of problems with constructed or calculated variables, such as if you look in nutrition, you may be interested in total energy, but also that comprises subcomponents of energy from different dietary aspects of the food, whether it's carbohydrate energy, protein energy, fat energy, or alcohol energy. Now, that's a different topic, compositional data problems. And even though composite variable bias and compositional data may sound similar, I just want to make it very clear that we're going to deal with composite variables today, which is where we create those variables. And maybe a future talk will address some of the challenges in causal inference for compositional data. So when we create variables, deterministic variables, we need to differentiate how we show them in a DAG. We would take the determined variables and put double lines around it. So the child variable here is fully determined, And then the parent variable or variables would have double arrows into them. And this is to separate the clearly determined variables, which cannot follow the usual mathematical rules and properties of DAGs, from the probabilistic ones, which can, for which we can apply all of the tools and abilities that we have in our toolkit of causal inference. So a simple derived variable, here I've chosen a continuous measure to be birth weight, can be thresholded, for example, either side of 4 kilograms to make a binary variable macrosomia. That's the very simplest example. More complex and totally relevant to obesity research is the BMI, which is a bit more complicated because we create a ratio variable of weight divided by height squared. Now, why does it matter? Well, inferential bias occurs with composite variables. What we mean by that is that if we don't treat determined variables differently and assume they're probabilistically related, then we're dragging in deterministic relationships that could overwhelm genuine causal relationships that we're interested in. If therefore, whatever we analyze with a mixture of deterministic and probabilistic variables without realizing this distinction, what we obtain is statistically correct, but inferentially meaningless. It's the inference is done in our head. We take the value that we obtain, which could be a conflation of the determined element defined by the deterministic nature of the variables, and conflate that with a true causal relationship that we're actually investigating, and we can't unravel the two. So that's what's meant by inferential bias there. It's not that the statistics are wrong, but the inferences given to the statistic is wrong. This is easiest to see with tautological associations. When, for example, we derive a variable and it's analyzed in relation to itself or part of itself, or perhaps less obviously, where we have purportedly two independent variables, but when we dig a little deeper, we find that each of them comprises something that in common, there's a common algebraic component. And if we analyze data in these situations, then the resulting statistic comprises some tautological association, as well as potentially meaningful causal association, but we can't separate the two. So if we just interpret that outcome as if it's fully causally meaningful, that's a tautological association. Potentially could be entirely tautological, and that's the mistake that we make. So tautological associations are perhaps more obvious. They're self-fulfilling, they're by definition created. They are considerably overlooked still, but they're easier to recognize. They were first pointed out over 100 years ago by the father of modern statistics, Carl Pearson, who coined the phrase spurious correlation, and he was referring to ratio variables, which I'll cover in a moment. But I think it's useful to use this concept of spurious correlation because it's not saying it's statistically wrong, it's just that the component of it isn't perhaps the part that you're investigating for. So a ratio variable is a very simple construct, and indeed a simpler version than BMI is that looking at percentage body fat. So it seems harmless enough to actually create a percentage or create a ratio in this situation. But the problem occurs where we examine quite a lot of proportions together. And this occurs, for example, in health geography, where we may be interested in the prevalence or incidence of specific conditions by geographical areas. So, for instance, if we were examining the number of people living with obesity across a geographical area, and we divide by the population of that geographical area to get the prevalence of obesity, that would be a small area measure that you could have quite easily calculated for health geography purposes. And then you look at other measures. You may be interested, for example, in the role of obesity leading to diabetes. But the problem is with the common denominator, N, the population. If the number of events of what you're interested in one exposure related to an outcome, occurs because both is driven by this population common denominator, then you effectively have confounding, right? So if we ask that question, the people with diabetes, are they at risk, increased risk of diabetes because of they have obesity. The confounding factor when you analyze this at a clustered or ecological level is the common denominator of population. And it's not infrequent that you see that it would be at that level that you ask the question of diabetes prevalence in relation to obesity prevalence. But the problem is that dividing by n creates this curious correlation, spurious correlation, which is an artifact. This can be readily identified when you look at the regression equation, right? So the outcome is divided by n, and the exposure is divided by n. So you see n's on both sides of the equation. So in a regression equation, if you're regressing one phenomenon on itself, you're bound to create a spurious component in the coefficient here, beta 1, that is an artifact, not real. So the solution, well, I would say all analyses should be informed by a DAG, but the solution is to think about this as we've already identified. It's a common denominator as acting as a confounder. So it's perfectly reasonable if you've got a confounding situation where n confounds the exposure and the outcome, to remove its spurious correlation or effects, you condition on it. And so by including it in the regression model like this, you see that you have n purely on the one side now. And this is fairly obvious from a DAG, if, of course, n is a true confounder. For the context, this might not work. So if we look at total local authority spending input and from the government, central government, and how much of that trickles through to, say, spending on care homes, that will depend on different regions according to the numbers of elderly and many other factors, of course, as well. But if you wanted to try and consider adjusting for that n, the point would be that it's a mediator, which can't provide the total causal effect. So a more complex approach is needed here, which we don't go into today, but it's basically mediation analysis. And the point, however, remains that you should still examine what best solutions are informed by your DAG. And unpicking the problem as a confounder may help, rather than treating it as a ratio. Now let's look at a different situation, one of change scores, and we'll do it again through the simple approach of a tautological association to make it easier to grasp the implications. So here we might ask the question, does change in an outcome relate to the baseline of that outcome? Well, the problem with that is that, as we can see again in the regression equation, is that we have baseline outcome in both sides of the regression equation, and that creates a spurious correlation. There may well be a genuine relationship between baseline and follow-up that's causal, but it'll become conflated with one which is entirely artifact. So this is an example of composite variable bias, which is fairly easy to recognize because it's a tautological association. And were we to infer that the estimate statistical that we calculated from this regressing change on baseline to be fully causally meaningful, we'd be wrong. So solutions there are basically to identify and avoid such tautology. Now, arguably, DAGs aren't essential for that. When it's tautological, it's usually quite straightforward to look at the formula alone. So you can see that in both change and in ratios, you've got common variables on both sides, and this is what creates the problem. But tautological associations are only the tip of the iceberg. They're easier to see. Having said that, they're still heavily overlooked. There's a hell of a lot of problems in the literature where they occur, and they shouldn't, because people don't think carefully about these things. But there are many situations which are far less obvious. And problems arise when we analyze deterministic variables, which we can't necessarily see as problematic unless we use DAGs to unpick the problems. So let's return to what we think we mean by change. What is exogenous change, as in external change in an outcome followed up over time? Well, future values of a variable y, y1, are obviously determined in part by its past values. That's the determined component. there'll be some measurement error and or biological variation, which usually gets conflated. And then what's left over is all non-random determinants of change, which is exogenous change, C1, as I've depicted it here. And it's in a circle because it's latent. It can't be obtained directly. But that's actually probably what we really want to consider when we're analysing change. So it's the element of the follow-up that's not determined by the baseline and the bit of noise as well, but that's usually unavoidable. So how do we get at that? Well, if we want to remove the effects of Y0, we condition on them. So the best estimate of C1 is obtained by taking Y1 and conditioning on Y0. And it will be an estimate, it'll have the noise element in there too, but it'll be a far better estimate than subtracting Y0 from Y1, because that isn't change. So unfortunately, change scores are junk, doesn't capture exogenous change. So instead of getting at the component of Y1 that isn't generated by Y0, we actually add in the minus component of Y0. So the reason change scores are so incredibly misleading is that we introduce this negative sign of the baseline within the composite outcome of change score. So why is that a problem? Well, this is an example where we can't see the tautology because it doesn't exist, but it is still a problem. So if we consider an exposure of interest that may affect change in our outcome, then regressing to the change score directly on that exposure doesn't appear to have any mathematical problem, because X is quite happily on the right-hand side only. The issue arises in observational data, not trial data, because if we have any relationship between X and Y0, the baseline outcome and exposure, then there's a spurious correlation between them, right? Because that could have been caused by confounding, common confounding. And that relationship then gets negated and added in to the outcome, the change score. So the relationship between the change score and the exposure contains that negative, spurious correlation. And it can be quite strong. If you're investigating the role of exposure X on the change in an outcome, presumably X has the opportunity to causally influence the outcome. So it could well be strongly related to Y0 in an observational setting. So the problems we face really with observational research is the lack of randomization to break these otherwise often unrecognized potential causal links due to common confounding back in the history, as it were, prior to the measurement of the baseline data. But it's worse than that, because we not only fail to recognize that potential problem of lack of randomization, but we don't even think about the variables carefully that we analyze. Are they composite? Should we deconstruct them? Well, the answer is, if you want causal insights, yes. If you're analyzing composite, you can't get causal insights. But we also have a very fluffy idea sometimes of what it is we're asking in terms of the research question. You might be interested in, say, adiposity or fat mass, but we don't explicitly have those measures. And this therefore leads to a lack of rigor around framing the research questions. So we may, for instance, be interested in adiposity, but we haven't directly measured it. So we argue that BMI is a good proxy for that, without realizing that we've just added more problems than we've solved by bringing all of those composite aspects of height and weight combined. We may have some fluffy notion about looking at change in some outcome over time in relation to other things, but we haven't defined robustly what we judge to be change. So we make change scores because it feels intuitive, not recognizing that we've just dragged in a whole raft of other problems. And worse still, I think, is that we often do all of this without necessarily achieving any objective that is causally motivated. Even though we might really desire causal inquiry, we throw a lot of sophisticated methods at data without thinking about them carefully and don't really provide any solutions that are causally informed. So many examples abound in the literature where I would say both the methods and data are not considered carefully, and this isn't challenged enough. And there may be, as a consequence, an absolute mass of literature out there, and I think we're drowning in it. Muddies the water, where what looks like sophisticated analyses are produced, but actually there's nothing of value generated analytically. So anonymously, I'll just give a couple of examples. And this study looked at change in diet, physical activity, and body weight. So it looked at change in everything, including BMI and percentage change in weight, and comparisons were then made between weight change groups or BMI change groups, whatever. So huge amount of composite variable analysis taking place. The statistical robustness of all of the estimates remains, but the interpretational utility is zero. But bizarrely as well, when you look at what comes of this, is that the outcome was, after all that hard work, that gaining weight and BMI occurs between high school and college. Really? That's a critical period, apparently. And then suddenly, out of nowhere, right at the very end, in the conclusion, the focus is targeted information may be effective in preventing this weight gain. Well, the problem here, as far as I see it, is that the heterogeneity is inevitable. Some people will change more than others. So there's nothing sophisticated or helpful in being teased out here. And the intervention wasn't even investigated. It was just mentioned as an afterthought. So there's nothing causally informative or valuable going on. So I'm not quite sure what the purpose of this study was. Even worse, perhaps, for those who attended the last month's lecture, here we have an example identifying adults at high risk of change in weight and BMI. Well, high risk groups being identified is a prediction problem, not a causal problem. And then they're interested in the relative importance of age, sex, ethnicity, region, social deprivation. Sounds like that would be a causal question, but unfortunately, were it pursued as such, even in a causal analysis, and analysing weight gain as the outcome wouldn't give you causally robust estimates. But it's actually a prediction problem. So there's no relevance to actually looking at the coefficients estimated in any of those covariates because they're meaningless. And what were the results of this study? Well, 18 to 24 years had the highest risk of transition. Again, interesting. Opportunity for population level prevention. Well, there's many opportunities out there, I'm sure. Identifying more at risk. Well, what are we going to do about it? And amazingly, the conclusion is a radical shift in policy is required, rather than perhaps a radical shift in the way we do science. Because at the moment, I see an awful lot of stuff like this, which is completely meaningless. So in summary, composite variable bias arises whenever two phenomena or more are combined into a single variable, and we pursue causal inference because the point is we can't then pursue causal inference. What we get out is rubbish. So change scores, ratio variables, and other complex constructs like BMI are junk. And if you're analysing them, you won't be able to ask causal questions because you're conflating too many component effects. So all phenomena must be separated and analysed as informed by a DAG. And we cannot overlook this complexity. For example, just a quick insight, if we look at BMI in relation to, say, cancer, it spans the life course, because if we're looking at BMI age 50, then weight at age 50 is confounded by physical activity, lifestyle, like diet, etc. prior to that, which are actually all mediators of height when height stabilized at age 25. So there's no statistical adjustment possible, so no causal inference is possible. And yet, regrettably, few studies legitimately try to do this properly, and yet we have the tools, we have the capability. So it's a complete waste of resource that we do not see proper causal analyses. So that's the end of my input.
I'll start sharing my screen now.
Okie doke.
Thanks, Ridda. If you do have any questions, please don't hesitate to pop them on Slido or in the chat.
Is the slide showing all right?
Yeah.
Okay. Yeah, so hi everyone, I'm Ridda, a PhD student in causal data science at the University of Leeds, and I'm supervised by Mark Gilthorpe, Andrew Praswich, and Jati. Today I will be presenting some work from a paper that I drafted for my PhD, which is titled Composite Variable Bias, Causal Analysis of Weight Outcomes. So this is just to give you an overview of what I will be covering in this presentation. So I will begin with the research background to provide you with the context for the study. I will briefly explain the main objectives of the study, and then I will describe the inclusion criteria for the dataset and explain the DAG-informed analysis. I will illustrate the key results, and then I'll conclude by providing you with the key take-home messages. So obesity researchers often analyze composite variables such as BMI, change scores, such as change in BMI and Z scores as outcomes in their analysis. This becomes problematic when the findings are used to make causal inferences because this practice combines multiple variables, so for example, height and weight, or follow-up and baseline into a single variable, which makes it impossible to untangle the causal role of each component variable, leading to a bias known as composite variable bias. As Mark said, analyzing composite variables is inferentially biased. It is worth noting that all composite outcomes present similar analytical challenges. So here I have provided you with some two examples. So Wu et al., for example, recently came up with a new index, the body roundness index, to capture the percentages of total and regional fat by combining height and waist circumference. Similarly, Krakauer and Krakauer came up with a body shape index using waist circumference adjusted for height and weight to examine abdominal fat deposit. Hence, this study focuses on illustrating these issues through a causal inference approach for obesity research by examining research into measures of body size over time. So we identified data sets with the following characteristics to demonstrate the bias that arises from analyzing composite outcomes. So first of all, we need a longitudinal study design to get the baseline and follow-up measures of individuals. And then in terms of age, it needs to be on adults as their height would have stabilized in early adulthood. And then we also need baseline measures as confounding measures for the key exposures of interest. We need the baseline height and weight, both for confounding of the key exposures and to generate the composite outcomes when combined with follow-up measures. And then minimum one main exposure of interest, such as psychological or socioeconomic status. The composite outcomes were generated using follow-up height and weight, with follow-up weight serving as the robust outcome. And then less than 10% missingness, because anything higher than that is likely to bias our analysis. Only the National Child Development Study, so the NCDS cohort surveys at ages 23 and 33 met the full inclusion criteria out of the 18 potential data sets that were identified through the UK data service. So the DAG-informed analysis helps to prevent the table 2 fallacy, which is the MINT's interpretation of the model estimate, when the same adjustment set is used for all the variables. Multiple regression is used where variables in the various models are informed by the directed acyclic graph, and a correct table 2 is produced where different models provide different causal inference estimates. All the analyses were conducted using the standard regression, so the LM package, linear model package in R within the RStudio platform. So the figure 1 here shows the DAG codifying how the variables are assumed to be causally associated with each other in the NCDS data, with potential outcomes are denoted in light blue, and all the exposures of interest are denoted in different colors to clearly illustrate the errors coming out of them. The order of the variables and the direction of the arrows are determined by the temporal order in which the variables stabilize. Ethnicity and gender stabilize at birth. Baseline height and baseline weight are used to calculate the baseline BMI, hence they precede this measure. Malaise score is a self-administered questionnaire that participants complete at baseline, so at age 23, to assess the psychiatric morbidity, for example, depression, at that time point. And in the DAG, this occurs after economic status, which is also measured at age 23, because economic status began stabilizing earlier than the Malaise score. The composite variables are fully determined. For example, BMI is fully determined by height and weight, and that's why it's in the double boxes. And this is, again, links to the Mark's talk, where he illustrated how we should denote this. And it's also worth noting that no other variables have arcs into the fully determined variables other than these, variables that actually help to create that variable. And there are no forward arcs from any fully determined variables. As you can see, there are no arrows coming off these variables, the one in double boxes, because their causal contribution is fully captured by the variable that helped to generate that variable. So figure 2 is just an example to illustrate to you how we can use the DAG to inform our analysis. So figure 2 here shows that to estimate the causal effect of economic status at age 23 on follow-up weight, we conditioned on these potential confounders, so ethnicity, gender, baseline height, and baseline weight, because these are the indicated confounders. So ethnicity is a potential common cause of both economic status and follow-up weight for this specific focal relationship. We did not, for example, condition on Malaise score because that is a mediator for this focal relationship. So Malaise score is on the causal path between economic status and follow-up weight. Figure 3 here visually illustrates the results from the DAG-informed models for the two exposures, so economic status and Malaise scores, to show the differences between the robust outcome, which is the first one, the follow-up weight, and all the other outcomes, such as follow-up BMI. When examining economic status and Malaise score as main exposures of interest for the impact on follow-up weight, baseline weight is a confounder, which allows the causal evaluation of the impact on weight change. Economic status and Malaise score are both binary variables that provide less information than a more detailed continuous variable, resulting in effect dilution as a result of dichotomization. Although the effect sizes of both the binary measure in the NCDS data were small, the analysis revealed subtle differences for the different weight outcomes. For example, the effect of economic status on follow-up weight and weight change is slightly higher than all the other weight outcomes, and the effect of Malaise score, on the other hand, is slightly lower for these. And for economic status, so the model 1 and model 3 give you the same answer because the chain models, so weight change and BMI change as outcomes, and follow-up models, so follow-up weight and follow-up BMI, they are mathematically equivalent when adjusted for the baseline outcome variable. The problem is we don't know which one is which. So when we are looking into these results, for example, the problem is we don't know which one is correct inferentially, as they are all correct from a statistical perspective. But the only one that provides a robust causal inference estimate is follow-up weight adjusted for the baseline height. So to conclude, the DAG-informed analysis of the NCDS cohort surveys at ages 23 and 33 shows that inferences differed across different weight outcomes. Differences in inferences in outcomes were observed between the two exposures, so economic status and Malaise score, and no consistency was observed. And the only robust causal estimate occurred for follow-up weight, with other outcomes occasionally even showing sign reversal. Instead of BMI, change in weight or any combination of these outcomes, follow-up weight condition of baseline height is required for robust causal inference regarding body mass. So the key take-home messages are that DAGs are required to provide a robust strategy for investigating the situation in which composite variables are correctly deconstructed and the parent variables are separately analyzed to disentangle meaningful causal relationships. And otherwise, inferences drawn from the analysis of composite variables may be significantly inferentially biased. The estimated value may not only be biased, but also of the incorrect sign. Here I have provided you with the key references. And in the next slide, I'll give you some recommended reading if you are interested in learning more about these concepts. Yeah, thank you very much for listening. I would be happy to take any questions you may have.
Thank you, Ridda, and thank you, Mark. We have got a few questions, but please, as I say, keep them coming either on Slido or on the chat. So the first question is for you, Mark. Of the various biases from analysing ratio variables or change scores, which is worse?
Well, that will depend upon the context. So I think if you took random numbers, X and Y, with the same variance or standard deviation, and differenced them and then correlated them with either, you'd get, mathematically, you can show that the correlation is 1/√2, which is 0.7, which is very high, purely out of random numbers when nothing's going on. But of course, if you're looking at follow-up measures, then it's Y0 and Y1, there will be a correlation between them. And as that correlation increases, the spurious component diminishes closer and closer to zero. But only when they're actually identical, which is therefore you haven't got a research question to ask, is the spurious component gone. With ratio variables, it's slightly different because if you took three random numbers, X and Y and N, all of the same variance, then X over N and Y over N are correlated when there's nothing going on between X and Y otherwise to the order of 0.5, which is perhaps not that big, but it's still half the way between 0 and 1. But that depends upon the degree of variation. So if N was constant, there wouldn't be a problem. But if N varies, then there's a problem. So if you're dividing through by populations of very similar size, then the effect is minimized, the biasing effect is minimized. So it's very context specific. And so you really can't be sure, and it's just best avoided, basically.
Okay, thank you. Another question for you, Mark. I'll try and keep these in the order of the talk if I can. Could you expand on what is inferential bias?
Okay, so if you look at the tools of mathematics and statistics as a black box process, there's a lot of focus about bias, meaning of bias, that's around that black box process. So if an estimate is biased statistically, then it means that if you repeat it an infinite number of times, the average will always be far from the truth, or from the, not the truth. So that's an example of statistical bias. However, if there are just random variations in data, and otherwise what you get at is repeated multiple times, and you get the average of all of those multiple estimates focus on the truth of what's being determined, that's not statistical bias. Now, what we're saying is that you can analyze data and provide a statistical estimate that is statistically unbiased, because what you've plugged in and what you got out gives you a meaningful statistical estimate. But the problem can be that that statistical estimate comprises both a true causal relationship that you're interested in, between, for example, obesity and diabetes risk, but it can also be a component which is driven by, if you're looking in small geographical areas, the structure, the population structure being driven by both. It's an artifact. So if you got an estimate, taking the example of ratio variables, of diabetes prevalence with obesity prevalence of 0.7, that doesn't tell you that the correlation is all causal. It could be that only 0.1 of that is causal and 0.6 of that is due to the spurious nature of having a common denominator of population. So the inference that you're making is biased. The decision you're drawn to in accepting as the estimate is biased from the truth that you were investigating. The statistics haven't betrayed you. You've plugged in the wrong things to get the wrong thing out. I hope that's a little clearer.
Yeah, and please, if anyone would like, do add so I guess, Mark, that links back to the point you kind of ended your part of the talk on about actually putting real thought into what your actual research question is and what you're actually doing and what you're plugging in and what you're getting out, which surprisingly is often quite overlooked. Okay, thank you. A question for you now, Ridda. How do we analyze an exposure of interest that precedes baseline weight?
Okay. I think as indicated, for example, Mark provided an example in his talk for care homes and cost of expenditure in care homes. You need to combine an analysis of both the exposure and
Ridda,
the baseline.
sorry, just because I think, Mark, it might be quite helpful if you can get that. Can you get that slide quite easily? Because I think to see it is
I'll have a look, yeah.
Sorry, perhaps everyone's brain doesn't work like mine, but I find it quite helpful to see these things while you guys are talking.
Yeah, sorry, I closed it down. Shouldn't have done that.
Oh, sorry.
No, it's all right. I've got it. Got it now.
Do you want me to bring your subject?
Yeah, I've got it now, I think.
Okay, so just for the audience, the question again was, how do we analyze an exposure of interest that precedes baseline weight? And I've directed it to you, Ridda, but both of you can kind of contribute or provide an answer.
Yeah. Yeah, so I think the problem there is, so you need to combine an analysis of both the exposure and the baseline height in what's known as causal mediation analysis, which is a very sophisticated method in itself, which we don't go through here. I think linking back to my own example as well. So for example, if you remember the diagram that I showed you, Mark, can you go through that?
Just about to bring that up, yeah.
Yeah, because it just makes it clear like why we need a different method. Yeah, so as you can see here, so the birth variables such as gender can only be evaluated as exposures for follow-up weight and not changes in body size, because baseline measures, for example, baseline BMI or baseline weight, they arise afterwards. So this comes before and they come afterwards in terms of the temporal order. And if you would use the traditional method, you would adjust for the mediator, which is wrong. So that's why we need to assess the impact on weight change. It is necessary to condition on baseline weight using causal mediation analysis, because you have to do the analysis of two joint effects of exposure in order to deal with that mediation properly. And if you are interested in learning more about the causal mediation analysis, I would recommend the Tyler van der Wiel's paper. Is called A Unification of Mediation and Interaction for Weight Decomposition, which goes through the further detailed explanation on how you should do the causal mediation analysis. But again, it's a very complex topic in itself, and that's why we don't go through that in this talk.
Yep.
Hey, Mark, did you want to add anything, or is
No, I think that was perfect.
No. Okay. I guess one other question, sorry, questions are coming at me from lots of different platforms here, and I think this follows on from some of the stuff you presented last week, Mark, so forgive me people in here, but is it true to say that composite variables do have a place from a description point of view when we're thinking about the 3 pillars of data science?
That's a very good question, and perhaps I should have emphasized it as such. The problem arises only in the analyses. So yes, if you want to report percentages or proportions and you want to describe things that are more intuitively understood, represented that way, descriptively, there's nothing wrong with creating constructs to represent your data. The problem arises purely when you then plug those constructs into analyses, because you can't then unpick the causal relationships of multiple variables being conflated into one. So it's purely the analysis approach that has to be careful rather than the purely descriptive approach. Yes.
Okay. And I guess that's all the questions from the audience. And I guess I think I know the answer to this, but I'll ask it for your your viewpoints with the audience, because I think if people are analysing secondary data, or in the world of big data, which we're now kind of ever finding ourselves immersed in, and taking opportunities to use these data sets that weren't created for research purposes, so haven't been through the rigor of the data generation process. If we only have these composite variables in there, so for example, we only had BMI, we didn't have height and weight, what would be your recommendation?
Do you want to go first, Ridda? What would you do? I'm putting you on the spot there.
Well, I put you both on the spot a little bit, but I think it's important that, you know, because we are presented with lots of different data sets across all different disciplines. Yeah. And
Okay,
I'll put myself on the spot. Sorry, I think sometimes researchers use it as an excuse of it was secondary data, so we only had this.
Yeah, so my answer is don't do it. If you haven't got the data that you need, you can't answer the question. It's the end of story at that point.
Yeah. I think instead of coming with inferences that are not meaningful, it's worth not doing the research that you know that it's going to be misleading, or it might, for example, it can be used for policy and other purposes which are very meaningful. And because there are people at the end of it, you don't want to come up with wrong inferences. So it's, as Mark said, it's better to avoid something. If you already know that it's going to be misleading and it's going to be wrong, why would you invest your time and money into something like that?
And it might sound very easy and flippant to say that, but actually it's a very serious point, because the problem is that people will still pursue their analyses on the grounds that it's all that was available. They'll say it wasn't perfect, but they'll wipe their hands of it, publish it, and then we could have situations where people come along and infer incorrectly that the estimates they provide are meaningful when they're not. So it's actually unethical and it's dangerous. And I hope last time we spoke last month, we pointed out that there can be serious harm caused by, doing the wrong thing. So it's actually, it's no use trying to put a clause saying, we did correlational analyses here, we didn't do causation, so you can't infer causation, because the question is, well, what the hell were you doing it for in the first place? And if what you publish isn't right, how useful is that? So I don't buy the argument that it's okay to do the second best if you actually no idea how bad it is.
Yep. No. Agree. Okay. Are there any other questions from people who are not me, basically, but for Mark and or Ridda? If not, I'd like to take the opportunity to thank Mark and Ridda for taking their time to pull the presentation together, but also to be with us today to present it. I think, there's lots of different people in the audience from different backgrounds. For some of you, this might be a bit of a revision and a recap, which is great. For some of you, it might be new and it might be quite daunting. And what I would say is if you are interested in kind of some of this methodological work, we are trying to push this quite a lot at the institute level in terms of the research we're doing, and we are happy to work with colleagues if you wanted more information, or like Ridda and Mark have signposted some reading and things today. But are there any more slides, Mark? I can't. Have you closed it down again? Oh, you're on mute. No,
I haven't, but I'm just going to bring up the crucial one you wanted to advertise, probably.
Yes, there you go.
Yeah, here we go. Oops. Yeah, there we go.
Yeah, and that kind of leads me into say we have now validated a new MSc in obesity, which will run from September 24. And it's it really truly is a transdisciplinary course, but it's underpinned by the methodological rigor supported by Mark and colleagues. So people on the call might be interested, but if you could also share that with your own colleagues and networks, it'd be really good to see a healthy cohort for that next September. Any others? And again, just a signpost really, if anybody on the call is interested in obesity and in disordered eating, colleagues in the Institute are working in this area and are establishing an international coalition. If you want to hear more about it, you can scan the little QR code there, or the information is on the screen. So don't hesitate to get in touch if it is an area you want to know more about. Okay, and then that just leaves me to say thank you very much for attending today. It's really encouraging and exciting to see such good numbers of people attending these seminars. Our next seminar is on the 29th of November, and it's around food marketing to young people and the impact on diet and implications for policymakers. So I hope to see you all then. Thanks again to Mark and Ridda, and I'll hopefully see you all in November.
Cool. Cheers. Thanks.
Bye.
Bye-bye.